A vertical descent down 265 meters of interlocking funnel-like columns. Most models classify this as a volcanic plug, but thermodynamic mathematics reveal a structural conflict. In structural physics, ideal hexagonal packing achieves a theoretical maximum cross-sectional density of 90.69%. It is the most energy-efficient geometry possible for dissipating stress. Using the thermal contraction stress equation with standard cooling magma constants, a Young's modulus of 60 gigapascals, and a temperature delta of 800 degrees Celsius, the resulting stress reaches 384 megapascals. This exceeds basalt's ultimate tensile strength by over an order of magnitude. Cooling fractures propagate to relieve this pressure, with tensile stress forcing primary cracks to initiate at 120-degree triple junctions. Standard cooling parameters dictate that these stress extremes result in extensive, irregular fragmentation. This predicts a chaotic debris field, rather than the 265-meter uniform vertical continuity observed here. Because thermodynamic heat loss laws in open systems do not resolve this geometric uniformity, the data requires a forensic comparison between the magmatic model and the alternative paleobotanical hypothesis of petrified biogenic structures. The biological hypothesis relies on a macro-scale structural convergence. The hexagonal jointing of these igneous monoliths closely mirrors the hexagonal vascular packing found in modern plant structures. This geometry is systemic. Global formations like the Giant's Causeway show identical proportions, suggesting a structural control mechanism independent of local volcanic chemistry. Specific morphological traits drive the biological classification: flaring dinguses that mimic root structures and vertical polygonal columns that resemble bundles of plant fibers. Standard geology classifies these formations as eroded volcanic laccoliths or magmatic plugs that solidified beneath the surface. In thick magma flows, internal thermal fluctuations typically produce chaotic, irregular fracturing known as entablature. This disrupts the uniform colonnade patterns below. This irregular entablature fracturing is a predictable result of an open thermal system, yet it is absent in the hyperuniformity required by the botanical model. Can a cooling rock mass achieve stability that perfectly simulates biological structural optimization, or does microscopic petrology disqualify this convergence? We can test the physical limits of both models by comparing the cooling front velocity of magma against the biomechanical hydraulics of capillary action. Isolating the time variable shows that cooling a 200-meter column requires over 10,000 years of continuous heat dissipation. The statistical probability of maintaining perfectly isotropic thermal stability without a single seismic or atmospheric disruption over a 10,000-year window is less than 1 in 10,000. However, the biological hypothesis faces its own biomechanical limits under the cohesion tension theory. Standard xylem physics caps maximum plant height at approximately 130 meters. Beyond this point, gravity and friction break the water column. Transporting mineral-laden sap to altitudes exceeding 500 meters would require hexagonal structural wall reinforcement to prevent vascular cavitation under extreme negative pressure. This requires an unmodeled biochemical environment, including an atmospheric pressure above 3 atmospheres and a hyperoxygenated atmosphere to support the necessary metabolic pathways. While the biomechanical model predicts the hexagonal geometry needed to avoid cavitation, its atmospheric requirements are not supported by the paleoclimatological record. To find a definitive answer, we must audit the taphonomic kinetics of permineralization, the process where monosilicic acid replaces organic matrices. During silicification, the original lignin-cellulose matrix degrades, but the organic framework acts as an exact template for the incoming minerals. Under scanning electron microscopy, authentic petrified wood preserves fine anatomical details. We see microcrystalline alpha quartz terminating at the middle lamellae, preserving distinct growth rings. The interior of these columnar monoliths shows a different structure. Polarizing microscopy reveals a purely crystalline texture, with sodium alkali feldspar and pyroxene phenocrysts that nucleated and grew from a silicate melt. There are no cell walls, no vascular bundles, and no organic carbon residues within this matrix. We find rocks composed of minerals like sanidine and anorthoclase. These are diagnostic of high-temperature magmatic origin and cannot form through low-temperature biological silicification. The microscopic structural architecture is entirely inorganic and crystalline, placing the botanical hypothesis at odds with the crystallographic evidence. A comparison of bulk elemental geochemical composition provides further clarity. We can map the chemical percentages of faunolite porphyry against silicified wood. This data shows that silicified wood is over 92% silica, while the faunolite columns contain only about 60%. The aluminimetrics show an even wider gap. Faunolite contains nearly 18% alumina, whereas petrified wood typically contains less than 0.5%. This elemental signature confirms the monoliths are highly alkaline, low-silica igneous rocks of magmatic origin. However, a critical data anomaly complicates this classification: trace organic carbon inclusions isolated deep within the columns. Standard igneous rocks contain trace carbon at levels below 0.03%, but samples from the interior column cores show concentrations up to 2.4%. The isotopic signature of these inclusions ranges from -22 to -28 per mil, values that are diagnostic of biogenic carbon. While bulk chemistry supports a magmatic origin, these deep-core biogenic carbon traces prevent a simple classification, demanding a wider systemic audit. Standard models define Devil's Tower as an intrusive body that's solidified beneath thousands of feet of sedimentary rock. This creates the volcanic volumetric deposition paradox. To expose this tower, over 1,500 meters of sedimentary strata must have been eroded with absolute precision. This level of erosion should leave a regional alluvial gravel bed filled with faunolite debris across the Great Plains. No such debris field exists. This lack of evidence extends to the contact metamorphism deficit. An intrusion of molten faunolite at 1100 degrees Celsius into host sedimentary layers must produce a distinct zone of hornfelsing and recrystallization, but the actual sediment boundaries show crisp, unbaked contacts. There is near-zero thermal alteration at the contact points. The absence of both an erosional debris field and contact metamorphism invalidates the stratigraphic requirements of the standard intrusive magmatic conduit model. To resolve these contradictions, geophysicists use deep lithosphere reflection models to map subterranean geometries. These 3D seismic reflection profiles reveal the structure does not terminate in a narrow vertical pipe. Instead, the lower terminus fans laterally into sedimentary beds. This lateral flaring correlates with deep-seated mafic sill complexes, providing a more accurate subterranean model than a vertical volcanic neck. This architecture aligns with UP geochronology, anchoring the structure to 1,073 million-year-old Grenville-age gabbro extensions. The deep sill model accounts for the missing surface debris, but it does not explain the biogenic isotopic anomalies or the thermodynamic requirements found in the exposed columns. While seismic tomography and micropetrology confirm magmatic architecture, the biogenic isotopic signatures and statistical improbability of 265-meter vertical fracturing remain unresolved contradictions in planetary petrology.